Okay, welcome back. 3.5, implicit differentiation. Okay, first off, what does implicit mean versus explicit? So most of the stuff you've dealt with to this point is explicit. So for example, something written like y equals 3x plus 2, this is explicit. In particular, if you could write it as y equals something, then it is explicit. Okay? So what's an example of something that's implicit that you've dealt with? Well, x squared plus y squared equals 9. Things like that. The equations of circles, the hyperbola, those guys are implicit. Okay, and that's the deal. Let's look at number 9. X e to the y minus 10x plus 3y equals 0. This is definitely implicit. All right. If you tried to solve out for y, I have no idea how you would even do that. It's like you can't even get it in an explicit version of this thing, even if you tried. The deal is though, you still can get a derivative for y. It's just the problem is going to be in terms of x's and y's. So this section will have a way of finding a formula for the derivative of y. It seems like kind of a bummer because you're not going to get this clean, explicit formula for the derivative. But it turns out it's okay. There's a happy ending to the story. It works. Okay, so implicit differentiation. And the way I've come to grips with it is to think of it as a chain rule, as an application of the chain rule. So in particular, for example, I have maybe, I don't know, some implicit function. We could take the circle again. X squared plus y squared is 9. What you're going to do is whenever you see expressions with regards to x, it's going to be derivative as usual. So the derivative of x squared, you bring down the 2x, and then 2 minus 1 is 1. Okay. For this thing, you do kind of a chain rule idea. Okay, so I'm going to take the derivative of this outer shell part. So bring down the 2 and then y, and then 2 minus 1 is 1. And then tack on the derivative of the y, the guts, so to speak. And you don't know what that is. It's kind of an unknown thing. Okay? You just tack it on right there, times the derivative of the guts. That's how I think of it. Okay? On the other side, the derivative of 9 is just 0. And then you could solve out for this thing, which is basically the derivative of y, which is what you're after. Okay? So you'd have 2y, y prime is negative 2x, and they could divide both sides by 2y. So y prime is negative x over y. And it seems like a bummer, like, oh no, I don't have a nice explicit derivative, in terms of x only. But this is okay. You can actually work with this, and it's fine. So note kind of here, and I think there's some exercises in the book where they go through this. They want you to differentiate explicitly versus implicitly. So this would be the implicit derivative. But if you did it explicitly, you can kind of make the connection between these two expressions. So in particular, you can solve for this thing explicitly. You'd say y squared is 9 minus x squared, and then y is plus or minus square root of 9 minus x squared. So you have two functions, and you can think of, one is y1 equals positive square root of 9 minus x squared. and then take the derivative of that. So y1 prime is 1/2 times 9 minus x squared to the negative 1/2 times the derivative of the guts, which would be negative 2x. Okay, so you get negative 2x times 1/2 is negative x, and then that's all over the square root of 9 minus x squared. And you sort of notice, well, hey, look, this is just equal to negative x all over y, in particular y1, right? Which is just this formula here. So you can always kind of make this connection if you could solve the particular formula explicitly. The problem is you're going to have to deal with guys like this, where you just cannot in any way untangle the y variable, and you're kind of stuck with just this implicit form. But you know, like I said, it's not bad. It's not that big of an issue. We can still work with it. Okay, so anyways, let's look at number 9 and take its derivative implicitly and then get a formula. So we have x e to the y minus 10x plus 3y is equal to 0, right? And we want to find a formula for y prime. Okay, so here I go. First, take the derivative of this. I need a product rule. Okay, so I'll have leave x alone, and then the derivative of e to the y is e to the y, and then times the derivative of y, minus the derivative of 10x is 10, and then plus the derivative of 3y is 3, and then times the derivative of y. On the right-hand side, the derivative of 0 is just 0. Okay, so what am I doing? I'm trying to solve for y, so I need to collect these guys together on one side, move the 10 over, so factor out the y prime, and then we could solve for y prime by dividing both sides by x e to the y plus 3. So I have 10 all over x e to the y plus 3. Okay, and then that's your formula. Okay. Let's look at another one. How about number 5? Plenty of examples for us. X cubed minus xy plus y squared is equal to 7. Okay, so the derivative of x cubed is 3x squared minus this thing, and we need a product rule, so leave x alone times the derivative of y. The derivative of y is 1, and then times y prime, plus leave y alone, take the derivative of x, which is which is 1, and then times the y, plus the derivative of y squared is 2y times y prime, and then the derivative of 7 is 0. Okay, so I have 3x squared minus xy prime minus y, and then plus 2y y prime is 0. Again, we need to collect all of our y primes on one side. Okay. So I'll rewrite it. 2y y prime minus xy prime equals y minus 3x squared. Factor out the y prime. So get y prime times 2y minus x is y minus 3x squared. And then divide by the 2y minus x. So y prime, in this case, you get y minus 3x squared all over 2y minus x. Good stuff. Let's move fast forward. Well, here's a bit of a nasty one. So 43, what we want to do is find the slope of the tangent line at the given point. Okay, so 43, they give us this guy, 3x times x squared plus y squared equals 100 times x squared minus y squared, and then the point is 4, 2. Okay. So we could sort of use a chain rule on this first guy, so I ended up with 6 times x squared plus y squared to the first power times the derivative of the guts, which would be 2x plus 2y, y prime. On the other side, we'd have 100 times 2x minus 2y, y prime. If you rather, you can distribute the 100, but you get the same answer. I want to collect all the y primes together, so I'm thinking I'm probably going to have to FOIL this thing out. So it doesn't seem like there's any nice way to say it, right? So yeah, let's go ahead and FOIL the critter out and see what we get. So it'd be 6x squared times 2x is 12x cubed. 6x squared times 2y prime plus 12x squared y prime plus 6y squared times 2x is 12x y squared plus 6y squared times 2y prime is 12y cubed y prime. On the other side, I got, looks like 200x minus 200y prime. And I'm looking for y prime. So I need to collect all these characters together. This guy, this guy, this guy. Push the other guys to the other side. So let's see. 12x squared y prime plus 12 is it y cubed? Is it really y cubed? Y cubed y prime plus the 200 y prime equals 200x minus 12x cubed minus 12xy squared. Factor out the y prime and divide. So I'm getting y prime equals 200x minus 12x cubed minus 12xy squared all over 12x squared y plus 12y cubed plus 200y. Okay, so that's our formula for the slope of the tangent line at any given point. In particular, we want to know the one at 4, 2, I believe. So what do? You just basically plug your point into this expression. So y prime of 4, 2. If you go through and do all the arithmetic, you should end up with negative 2/11. Okay? Okay, great. One thing then, working with implicit differentiation, that we'll be able to do is find the derivatives of all the inverse trig functions. Okay, so that will be awesome. Let's go ahead and attack that. And we'll follow, if you want to follow along, this is example 6 in the book. And find basically the derivative of sine inverse. So if we start with if we start with y equals sine inverse of x, I can take sine of both sides of this equation, and I'll have sine of y equals sine of sine inverse of x, right? So I could take sine of sine inverse of x, and I'm left with sine of y equals x. Okay. Now I'm going to take the derivative implicitly. So the derivative of sine y will be cosine y, and then you tack on your y prime. On the right-hand side, the derivative of x is 1. So if you note, what we're going to be able to do is solve for y prime. And that's important because y prime is the derivative of sine inverse. And that's what we're after. Okay, so divide both sides by cosine y. We are going to restrict, use a restriction on cosine. So we'll restrict cosine to be from negative pi over 2 to pi over 2. Okay, so we want the inputs of cosine to be y is in this interval from negative pi over 2 to pi over 2. So for one thing, we don't want cosine to equaling 0. Also, another thing is we're going to replace cosine of y. Okay, so cosine of y, if you think about the Pythagorean identities, I want to rewrite this in terms of sine. I can do that by noting that sine squared y plus cosine squared y is equal to 1, which tells me that cosine squared y is equal to 1 minus sine squared y. And then cosine of y is equal to plus or minus square root of 1 minus sine squared y. But if y is in this interval, then the cosine of y will have to be positive. So we just have the positive root. Okay, so now this allows me to rewrite this, and you'll get y prime is equal to 1 all over the square root of 1 minus sine squared y. And then sine of y, we said, was equal to x. So I can replace this expression with something that is algebraic, 1 minus x squared. We get rid of that nasty transcendental function sine y. So it's, if you have y equaling sine inverse of x, its derivative, which we'll need to have encoded into our brain somehow, is 1 minus 1 over 1 minus x squared. Okay, and we'll probably be investigating that more later. Okay, let's move on to the last topic here is logarithmic differentiation. Okay. So sometimes you'll have these really, really nasty looking expressions. You want to figure out the derivative, and what you could do, the cheat, is to take the log of both sides. Okay. And then differentiate implicitly, and then solve for the derivative. Differentiation, logarithmic differentiation. Okay, there are some assumptions. You have to assume that this y is greater than 0, so it fits in the domain of the log. And then it's kind of, business as usual. Anyways, let's say it's 65. We have y equals x times the square root of x squared plus 1. And we'll presume x is greater than 0. Okay, okay. So by itself, this would be kind of nasty. You would have to do a product rule and a chain rule on top of it, and you just get this nasty looking expression. You could do logs, though. Okay, so take log of both sides. ln of y equals ln of x times the square root of x squared plus 1. And then we can use the rules of logarithms to expand this. So I'd have ln of y equals the natural log of x plus the natural log of x squared plus 1 to the 1/2. Okay, and then I could use a power rule to bring this in front. So I have the ln of y equals ln of x plus 1/2 ln of x squared plus 1. And then you can differentiate implicitly. So the derivative of ln of y is 1 over y times y prime. The derivative of ln of x is 1 over x plus 1/2 times the derivative of ln of x squared plus 1 is 1 all over the guts times the derivative of the guts. Okay. You're going to want to multiply both sides by y to isolate y prime, right? So I have y prime is y times 1 over x plus 1/2 times 2x is just x. So we have x all over x squared plus 1. And then we can actually get this in terms of x, right? If we back substitute this expression for y into here, we end up with our final derivative. Y prime is x times the square root of x squared plus 1 times 1 all over x plus x all over x squared plus 1. Okay? You can distribute, make it look real pretty, but that really does the job, I think. And we'll leave it there. Okay, thanks for watching. Bye.